It is November 2025. For astronomers and space enthusiasts alike, the past few months have felt like waking up from a long, blinding dream. For decades, humanity's view of its own star was paradoxically obscured by the sun's own brilliance. We could see the surface, the photosphere, in exquisite detail. We could see the far outer atmosphere, the outer corona, billowing into the solar wind, thanks to instruments that blocked the sun's glare. But the critical middle ground, the inner corona, remained hidden in the glare. This is a region of fire and mystery, where the solar wind is born and where the temperature inexplicably jumps from thousands to millions of degrees. It was a region visible only during the fleeting, chaotic minutes of a total solar eclipse on Earth. That changed this year. In June 2025, a pair of satellites flying in a high-stakes formation, 150 meters apart, beamed back an image that solar physicists had dreamed of for a century. They captured a perfect, stable, high-resolution view of the sun's inner corona, not during a rare earthly eclipse, but on demand, from the vacuum of space. This was the triumph of Proba-3, the European Space Agency's boldest technology demonstrator to date. Proba-3 is not just a solar observatory, it is a feat of engineering choreography. It consists of two separate spacecraft, the coronagraph spacecraft and the occulter spacecraft, that dance through the cosmos with such precision that they function as a single giant instrument. By casting a precise shadow from one satellite to the other, they create an artificial eclipse that lasts for hours, unlocking the secrets of our star's atmosphere and paving the way for a future where giant telescopes are not built, but flown in formation. To understand why Proba-3 is such a monumental achievement, we must first understand the problem it solves. The sun is a deafeningly loud object in the electromagnetic spectrum. Its surface shines with such intensity that it washes out everything around it. Surrounding the sun is the corona, a tenuous atmosphere of plasma that extends millions of kilometers into space. The corona is millions of times fainter than the solar disk. Observing it is like trying to see a firefly hovering next to a stadium floodlight. For most of human history, the corona was a ghost, appearing only when the moon serendipitously slid in front of the sun. These total solar eclipses were transformative events, revealing the pearly white halo of the corona to awestruck observers. But they were short. The longest possible eclipse lasts about 7 minutes and 30 seconds. Most are much shorter. An astronomer might spend an entire career chasing eclipses and accumulate only an hour of total observation time. In the 1930s, French astronomer Bernard Liot invented the coronagraph, a telescope with an internal disk to block the sun. He climbed to the top of the Pic de Midi in the Pyrenees to escape the scattering of light by the lower atmosphere. It worked, but only partially. The Earth's atmosphere still scattered enough sunlight to wash out the faint inner corona. The space age brought a solution, which was putting the coronagraph in orbit. The SOHO spacecraft, launched in 1995, carried the LASCO coronagraphs, which revolutionized our understanding of the sun. However, traditional space coronagraphs have a fatal flaw. Because the blocking disk, or the occulter, is inside the telescope tube, sunlight diffracts or bends around its edges, creating stray light that floods the detector. To prevent this, engineers must over-occult, blocking not just the sun, but a large part of the inner corona as well. This created a blind spot. We could see the sun's surface. We could see the outer corona. But the region between the surface and two solar radii, the very place where the corona heats up and the solar wind accelerates, was lost in the glare. The only way to see this forbidden zone without waiting for the moon is to move the occulter far away from the telescope, just like the moon is far from Earth. If you place a disk 150 meters away from your camera, The diffraction around the edges is minimized, and the shadow is deep and dark. But how do you hold a disk 150 meters in front of a telescope in space? You cannot build a boom that long. It would be too heavy and wobbly. You have to fly two separate spacecraft, and they must stay aligned perfectly. If the shadow shifts by just a few millimeters, the blinding sun hits the telescope, frying the sensors and ruining the science. This is the challenge of Proba-3. Proba-3 is a mission of firsts. While spacecraft have docked before and flown in loose formations, no mission has ever attempted precise formation flying, with unrelated spacecraft acting as a single rigid structure for optical science. Let's look at the duo. First, there is the Occulter spacecraft, or OSC. It is the leader of the dance. It carries a 1.4-meter diameter disk with a razor-sharp edge. Its job is to face the sun and cast a shadow. It is the smaller of the two, weighing about 200 kilograms. Then there is the Coronagraph spacecraft, or CSC. This is the follower. It carries the ASPIICS instrument. It lurks in the shadow cast by the OSC, 150 meters behind it. It weighs about 340 kilograms. The pair was launched on December 5, 2024, by an ISRO PSLV-XL rocket from India. They were injected into a highly elliptical orbit. This orbit is crucial. At perigee, the closest approach to Earth at roughly 600 kilometers, gravity is strong, and the Earth's pull varies rapidly. Formation flying is impossible here due to fuel costs. But at apogee, the farthest point at roughly 60,530 kilometers, the spacecraft moves slowly and the gravitational gradients are weak. For roughly 19.7 hours, which is one orbit, the satellites drift loosely. But as they approach apogee, the dance begins. For 6 hours, they lock into formation. The OSC creates the shadow, and the CSC hunts for the center of that shadow. Now, how do two boxes in space know their relative position to within a single millimeter? Proba-3 uses a multi-stage metrology system, a hierarchy of senses that gets sharper as they get closer. First, there is relative GPS, like your phone finding its location, but relative to each other. This gets them within a few centimeters. Next is the visual-based system. Cameras on the CSC look at the OSC. The OSC is equipped with LEDs acting like stars in specific patterns. By analyzing the image of the OSC, the CSC knows its orientation and range. This brings accuracy down to the millimeter level. Then comes the fine lateral and longitudinal sensor. This is the magic laser. A laser beam is fired from the CSC to a corner cube retroreflector on the OSC. The time of flight gives the distance with micron-level precision. The angle of the returning beam gives the lateral position. Finally, there is the shadow position sensor. This is the ultimate check. Sensors around the telescope lens on the CSC measure the edge of the shadow. If the shadow drifts, these sensors detect the sunlight peeking around the edge and tell the computer to correct immediately. The most terrifying aspect of Proba-3 is that it is autonomous. The distance to Earth means there is a signal delay. If the formation breaks, ground control cannot save it in time. The satellites must think for themselves. The onboard software runs a continuous control loop. If the CSC detects it is drifting 1 millimeter to the left, it fires tiny microthrusters to scoot back to the right. It does this continuously, thousands of times, fighting the subtle tug of gravity and solar radiation pressure. To the data recorder, it looks as if the two satellites are connected by a rigid steel beam. In reality, they are connected only by light and code. The launch in December 2024 was flawless. The PSLV-XL roared into the sky over Sriharikota, depositing the stacked pair into their elliptical orbit. But launch is only the beginning. For weeks, the two satellites remained clamped together, undergoing health checks. Then came separation. In early 2025, the clamps released. Springs pushed them apart. For the first time, they were two independent bodies. The mission control team at ESA Center in Redu, Belgium, held their breath. If the propulsion system failed now, they would drift apart forever. The months of March, April, and May 2025 were a period of intense anxiety and methodical testing. The team tested the collision avoidance maneuvers. Since the satellites fly so close, the risk of a crash is real. They verified that if a sensor fails, the satellites would instinctively fire thrusters to drift safely away from each other. In May 2025, the critical moment arrived. It was time for the first full formation flying test. The command was sent. The Eclipse spacecraft maneuvered 144 meters, then 148 meters, and finally 150 meters. It stopped. The coronagraph spacecraft locked on. The lasers fired. The relative velocity dropped to 0. They held it for an hour, then 2, then 6. They were a single machine. With the formation proven, it was time to open the eyes of the ASP-IICS instrument. The shutter opened on June 16, 2025. The first images were breathtaking. They showed the sun as a black disk, the occulter, surrounded by a ghostly, complex halo of green and white light. Proba-3 captured the corona in the light of highly ionized iron, known as the green line, at 530.3 nanometers. This green line is a fingerprint of extreme temperature. The image showed loops of plasma snapping and twisting just above the surface, features that SOHO could never see because they were hidden behind its internal occulter. The diffraction limit was broken. The shadow was deep. The stray light was practically non-existent compared to previous missions. Proba-3 was seeing the corona starting at 1.1 solar radii, almost hugging the surface. Now that Proba-3 is operational, the scientific community is feasting on the data. They are looking to solve 3 specific mysteries. First is the coronal heating problem. This is the holy grail of solar physics. The sun's surface is about 5,500 degrees Celsius. If you move away from a fire, it should get cooler. But as you move into the solar corona, the temperature skyrockets to 1 to 3 million degrees Celsius. There are 2 main theories. One believes in nanoflares, millions of tiny magnetic explosions happening every second that heat the atmosphere. The other believes in Alphine waves, magnetic waves that carry energy up from the surface and crash in the corona like ocean waves, dumping their heat. To distinguish between these theories, you need to see the magnetic structures in the inner corona where the heating happens. Proba-3's high-resolution, close-in views are finally allowing physicists to track these waves and nanoflares in the crucial heating zone. The second mystery is the birth of the solar wind. The solar wind is a stream of charged particles that bathes the entire solar system. It causes auroras on Earth and shapes the environments of all planets. We know it accelerates to supersonic speeds, but we don't know exactly where or how it gets that initial kick. Proba-3 observes the specific region between 1.1 and 3 solar radii, where the solar plasma transitions from being trapped by the sun's gravity to escaping as the solar wind. It is watching the wind being born. The third mystery involves coronal mass ejections, or CMEs. These are massive eruptions of billions of tons of plasma. If they hit Earth, they can cause geomagnetic storms, knocking out power grids and satellites. Current early warning systems rely on coronagraphs that have a blind spot. We often don't see a CME until it has already traveled a significant distance. Proba-3 allows us to see the initiation of CMEs, the moment the magnetic field lines snap and the bubble of plasma detaches. This data is vital for improving space weather models and giving Earth earlier warnings. The legacy of Proba-3 will extend far beyond solar physics. It is a gateway mission. By proving that 2 spacecraft can fly with millimeter precision, Proba-3 has validated technologies that will revolutionize astronomy. One of the biggest dreams of astronomy is to take a picture of an Earth-like planet around another star. But stars are billions of times brighter than their planets. We need to block the star's light to see the planet. This requires a star shade, a giant, flower-shaped screen flying tens of thousands of kilometers in front of a space telescope. It is essentially a supersized Proba-3. NASA's proposed Habitable Worlds Observatory may utilize starshade technology. Before Proba-3, critics argued that formation flying was too risky and precise for such a mission. Proba-3 has silenced the critics. It has proven that the dance is possible. Then there is X-ray interferometry. In the future, we want to see black holes and neutron stars, with detail 1,000 times sharper than the James Webb Space Telescope. This requires interferometry, combining light from multiple telescopes. On Earth, we do this with fiber optics. In space, we can do it with formation flying. Imagine a swarm of mirrors flying kilometers apart, beaming light to a central collector. They would act as a telescope, with a lens kilometers wide. The guidance, navigation, and control algorithms refined on Proba-3 are the ancestors of the software that will run these future giant observatories. The ability to rendezvous and hold position autonomously is also crucial for Mars sample return and orbital servicing. Future missions to Mars will need to catch samples launched into orbit. Satellites in Earth orbit will need to be refueled or repaired by robotic servicers. The sensors and logic refined on Proba-3 are directly applicable to these operations. As we look at the green line images streaming down from Proba-3 in late 2025, we are looking at more than just the sun. We are looking at a paradigm shift. For 60 years, the word spacecraft meant a single object, a metal box with antennas. If you wanted a bigger instrument, you had to build a bigger box and a bigger rocket to launch it. Proba-3 has broken that chain. It has demonstrated that a spacecraft can be a swarm, a collection of independent parts acting in unison, connected by nothing but light and logic. It has turned the vacuum of space from a void into a structural element. The artificial eclipse is no longer a dream. It is a daily routine, a 6-hour precision waltz performed 60,000 kilometers above our heads. And in the shadow of that waltz, the secrets of the stars are finally coming to light.